Yep, we're live.
I'm good.
Good morning. Welcome. I'm Dan Kotichek. I have the honor and pleasure to be the faculty host for today's seminar speaker. More about Dr. Al Rizzi shortly. I have important information that I have to relate to. Previously recorded talks in the series can be found on the GRASP YouTube channel. If you're joining this talk via Zoom, please make sure to submit your questions if you have them via the Q&A button at the bottom of your screen, and they'll be answered by our wonderful panelists whom I'll introduce shortly. If you're here in person, then raise your hand and our panelists will go around and give you the mic, and it'll be yours to ask with. Make sure that you're holding the mic so that everyone, not only in the room, but also online and for posterity, will be able to hear your amazingly insightful and important questions. I would like to introduce our student panelists, Ms. Bibit Bianchini and Mr. Shane Rosenlevy, who will be conducting the question and answer period at the end of the talk. It's now my great again, honor and pleasure to introduce Dr. Al Rizzi. Al received his PhD from Yale University in 1994. He did a postdoc at University of Michigan for 2 years and then joined the CMU faculty in 96, right? A decade later, joined Boston Dynamics as the chief scientist. He stayed there until 2022, and he moved to the Boston Dynamics AI Institute, where he now serves as the chief technology officer. Al is responsible for a number of very, very influential papers from the mid 90s to the mid aughts. He, for example, he invented a notion of sequential composition, which is widely used and cited. He is responsible for the first visual servoing on the first legged running robot outdoors. He's responsible for the control algorithms that ran the first legged machine that could climb vertical surfaces, hard vertical surfaces outside. He has a number of very influential papers from that decade. Strangely, in 2006, the record becomes very silent. Strangely, some of you may be familiar with the cheetah, not the MIT cheetah, the Boston Dynamics cheetah, which depending on which machine at what day of the week you measured, it still has the world record speed for between 20 and 30 miles an hour. Some few of you may have heard of an obscure robot called Spot. Some of you may. Dr. Rizzi is responsible for the project that brought Spot to the world. Anyway, we just haven't seen too much of Al in the scientific literature, but we're now hoping that that might change with his shift from science officer in a technology house to technology officer in a science house. Let's hope that we hear and see much, much more from Al. Al, welcome. Wonderful to have you.
Thank you very much, Dan. For those who don't know, Professor Kotichek used to be my academic advisor when I was a graduate student. And he has been chagrined at me since 2006 when I left academia. The transition in 2006, well, what didn't happen in 2006, it was about 2 years later that we stopped worrying about publications and counting citations, and we started counting YouTube hits and thousands of hours of humanity that we had wasted by people watching robot videos. Just to confuse these things a little bit and to be a little bit clear, the place I work now is called formally the Boston Dynamics AI Institute, but we are not part of Boston Dynamics. We're a standalone entity. We're a completely separate company, completely separate mission. We're now trying to at least temporarily rebrand ourselves as just the AI Institute. So what is this AI Institute place, right? What's this all about? We're really trying to create the world's premier research institute that's going to focus on solving the most important and fundamental challenges in robotics and embedded AI. We really think this is a key step forward for all of these technologies, and that if we can pay attention to how to build capable robots that are in turn attached to cognitively smart embedded AI systems, we can actually move the needle and build systems that are capable of having a lot of impact on the world at large. So just a little bit of PR at the front. This is a picture of the building that we're located in. Yes, it says Akamai on the front of the building. Who knows who Akamai is? Wow, nobody, that's amazing. Akamai are the guys who in about 2000 decided they were going to make the internet work. They're the people who are responsible for doing distributed data storage on the edge of the internet so that all the web pages you go to work quickly. They built this building they finished building the building in 2019. Actually, it was November. So they started to move everybody in, and then they told everybody to go home in March. And then 2 years later, they said, hey, who wants to come back to our cool building in Kendall Square in Cambridge? And none of their employees wanted to come back to their building. So they decided they needed to lease out part of it. So we actually leased 4 floors in this building. It's actually a gorgeous space. It's a brand new building, and it's in a great location. We're about 2 blocks away from MIT. Obviously, it was built as an office building for an internet company. We're trying to turn it into a robot lab. So we're in the midst of doing a bit of remodeling. So these are just some architects' renderings of what one of our lab spaces will look like and what our primary reception area is going to look like when we're done. That ought to be about 9-10 months from now. We are a growing organization. So we've been in business really for just over a year now. And in that year, we've managed to hire about 140 people total. So we have a research staff of about 50, engineering staff of just under 50, couple drone execs and admins like myself who keep us functional, a bunch of people that we've, in the process of hiring, as well as a group of visiting faculty members. So there's a group of about 10 or 11, depending on how you count, who come and spend time with us on a weekly basis, ranging from a day a week to some people who are spending 4 days a week with us. And then over the course of this summer, we had a relatively large group of interns, some of whom I actually see in the audience here today. It's great to see you again. Roughly speaking, we have about 40 to 45% PhDs, about 30% masters, and then the rest are, bachelor's and technical degrees. Okay, how did we get here, right? What's happened, for Dan's sake, since 2006 when I left Carnegie Mellon? Well, we started with a lot of motivation, right? So this is a video that goes through basically a lot of things that have motivated us over the years to think about how can we build machines that really work in our world? And we used to watch these pictures of quadrupeds locomoting over extremely difficult terrain, running at extremely high speed. This was the motivation for the cheetah robot that Dan was talking about. We've looked at people, right, locomoting over complicated terrain, performing, gymnastic, athletic stunts, right, and doing that in structured and less structured environments. Right? And people are phenomenally good at this, right? People do it with their feet, with their hands, right? They're locomoting over spaces that obviously weren't designed to be locomoted over. And I don't know that we want to build machines that do this, but I sure like to build machines that were capable of that. And, here we are. This is actually Mark Rabert's grandson demonstrating some locomotion and cognition. Right? It's like, oh, no, that's not quite right. And this is at the age of, I think he's about 2 years old when he's doing this, right? So why are our machines so bad at this, right? Why are people so good and machines struggle to do these things? Okay, so 2006, I moved to Boston Dynamics. This is a little montage of things I've been involved in when I was there. The thing on the top left is the very first project I worked on there, which was a robot called Little Dog. There was a pen group that participated in this. The program that robot was built for and used it. The top right is a machine we used to call Sandflea. And the thing that was interesting about that was it was a very simple little differentially steered wheeled vehicle, but it had one trick up its sleeve, and it had a leg in it, and it could use that leg to jump. And then the video in the bottom left, that's the cheetah robot. This is the outdoor version of it that Dan alluded to. And that's a machine that ran at about 20 miles an hour, across a moderately flat parking lot. And then the video at the very bottom right, that's the original prototype for what is now the Spot robot, right? And that's about, that video is probably about 8 years old right now. And you can see it with its predecessor, right? The predecessor was structurally different in that it used hydraulic actuators, whereas the smaller version is an all-electric machine. Much more similar to what's in the world today is the product from Boston Dynamics. Okay, so what's in common here, right? These are all well-engineered mechanical systems, right? There was a group of smart mechanical engineers who worked closely with a group of software engineers and control systems engineers to figure out how to balance problem solving and figure out how to build these integrated systems that could actually do something that was demonstratable in the world. And that was always our goal. At Boston Dynamics, the goal was, oh, let's build systems, let's do research, but let's make sure that research culminates in a demonstration that we can show to people. Maybe we'll make a YouTube video out of it. Some of those YouTube videos will garner, 100 million views, which is weird. It's weird when, I go home and I talk to my wife, who at the time was involved in dog training, and she says, oh yeah, I sat with my friends at this dog training thing, and this person across the table said, oh, have you seen this video of this robot dog thing? And she's like, oh yeah, I've seen that. I know who does that. Okay, so, but there's a measure of success and impact there that I think is relevant, that getting these demonstrations to a point where they actually can reach out to and touch society at large is actually an important accomplishment, because it is a way to educate people about what these machines are capable of. So just a little bit about where Boston Dynamics is now. This is the other guys. They have an office in Waltham, Massachusetts. We're the guys with the office in Cambridge. So, they are productizing Spot. They are selling Spot. When I left a year ago, I think there were about 1,000 of them that had been sold. I think at this point, they're up to 1,500 or so that are out in the world. What is Spot? Spot's a platform, right? Spot delivers mobility that you can use as a researcher or customer to then go put your technologies on top of it, right? So it is really a service of a mobility service for hardware and software payloads that people might put on those machines. And that includes an arm, high performance cameras, navigation platforms, and computational platforms. The last year at Boston Dynamics, I spent a lot of time working with a small team on basically the manipulation functionality. So how do we deliver a mobile robot with a relatively high performance arm on it in a way that's actually usable by customers? So, you can do cool things like jump rope. You can send the robot out to pick up trash. This is pandemic times. This is one of the guys who was working for me who was living at the time in Western Massachusetts. Cool thing is we can give him a robot to take home, and he can program the robot to go pick up the trash he conveniently left in the driveway. The arm is functional enough, that the robot can actually drag a full-size cinder block around in a parking lot. The whole thing is accurate enough, reliable enough, repeatable enough that you can do parking lot scale art with the robot. So what are we doing at the AI Institute? Well, we're trying to combine that type of athletic capability, the mechanical capability of the machines, with a new capability that's focused on what I'm going to call cognitive intelligence, the ability of these machines to effectively reason about the world that they're operating in, understand it, do things that are actually useful for us. Spot's a cool robot. Over the last year, since I'm sort of detached from Boston Dynamics, I get slightly more honest assessments from customers who have those robots. And I think 201, everybody has said, oh yeah, this thing is great. It's very reliable. It works. It falls down. It gets back up. It keeps working. It does what I expect it to do. And then they complain that Boston Dynamics didn't open certain interfaces to the thing. And I go, yep, sorry, I don't work there anymore. So what are the areas we're pursuing at, oh, I'm sorry, I was going to conclude that by saying, but the missing part is it's not capable by itself in the environment. Some smart person still needs to program the robot, right? Some robot expert needs to be involved in helping the thing navigate, building software tools to make the thing navigate, make it actually touch the world and do something. To date, the robots are mostly getting used as inspection systems. So they're getting used to allow people to autonomously walk a robot through what would be a difficult space for a wheeled or tracked robot to navigate in and go collect data from their facilities, right? This is happening in the brewing industry, in silicon foundries, oil and gas industry, electrical distribution facilities. They're all very interested. They all have difficult environments and need to collect data out of those environments. But part of the barrier to real adoption of those things is the complexity of programming them. And so one of our focuses at the AI Institute is to try to address that, right? So how are we doing that? Well, we're focusing on 4 gross areas. The first is cognitive artificial intelligence. How do we make robots and embodied AI systems smarter? How do we actually give them some notion of common sense, right? Athletic artificial intelligence, how do we make machines more capable physically? A lot of the performance that you see in those old Boston Dynamics videos comes from a really smart balance between what was programmed into the machines and what was actually built into the mechanism of the machine. There's lots of tricks with using passive elements, spring elements, and things like that to make the machines very, very capable. We're very interested in what we refer to as organic hardware design, really using advanced design techniques as well as materials techniques combined with computational methods to do better mechanical, electrical, and sensor and perception design. And then last, and still very, very important, is worrying about issues related to ethics, policy, and safety. Because it's not enough for us to build these technologies and make cool videos. We actually have to make sure people understand what they're seeing in those videos and that they understand how to use the kinds of technologies we're producing in an appropriate way that they actually help society at large, because that's really what we all want to do, right? We want to make life better. Well, if the people on the other side, we can't just throw this stuff over the fence. The people who receive this, the people who write laws around it, the people who are going to write policies have to understand what these technologies are, what they're capable of, and how to incorporate them into society. So at the AI Institute, we like to think of ourselves as sort of sitting between what I would call a traditional academic environment and a traditional corporate research lab, right? we're very interested in doing all the things you see in the bullets here, right? Thinking fundamentally about problems, working on novel and futuristic ideas, moving technology forward, being open and very collaborative with people. At the same time, we want to do that in a setting where we really encourage teamwork. We think a lot of the innovation that is important to move these kinds of technologies forward comes from combining thought from very different disciplines. We want to have experienced and stable staff. If you're, well, a market experience I had moving from the academic world to the corporate/industrial world was, it was amazing to have professional technicians in my lab. Things that broke didn't have to get fixed by the grad student at 3 in the morning. There was somebody who was professionally responsible for fixing it. And I used to be the grad student who fixed things at 3 in the morning. And, you know, yeah, that's hard. It's really, really hard in an academic setting to have what I would call systems engineering thinking, to think about sort of the entirety of the system and the implication of one piece on another, right? In an academic setting, everybody is pretty much encouraged to focus on their component of the technology. And it turns out, I think, especially in robotics, that this is an important idea if you're really going to innovate. You have to think about trade-offs between what you solve in software, what you solve in a control system, what you solve in a design problem. And then finally, we think it's super important to do projects at a meaningful scale, that you need to put together a completely integrated system, get to that complete demonstration of probably not a complete product, but at least something that's viable and understandable by a non-technical audience to explain what's possible. How do we do this? We hire a lot of people. As I said, we're already up over 100 full-time employees. But we do this by hiring people across a broad spectrum, right? So yes, we hire a lot of roboticists, lots of engineers, computer scientists, designers, you know, predominantly mechanical and electrical designers. We hire technicians, right? People who are going to fix things, make things work, and be professional about that. We hire fabricators, you know, people who know how to use machine tools and do welding. In contrast to what we do at what we did historically at Boston Dynamics, we're hiring postdocs, so people who are going to work with us for a finite period of time, focus on moving some of the technology forward. And then again, as I mentioned earlier, we have a relatively aggressive program to engage with interns. Mostly at the graduate school level. We had a group of undergraduate interns who worked with us this summer. I think that went really, really well. And we're going to continue doing that. For everybody who's thinking about getting a job in the next year, there's the link. Please don't hesitate to visit. I'm obliged to put in a couple plugs for us. Again, also in contrast to what we used to do at Boston Dynamics is we have a relatively active program that's collaborating with university participants. So there's both collaboration efforts and funding activities that are going on here. As I mentioned earlier, we have about 10 visiting faculty who are actually spending time at the Institute on a weekly basis. And then we have about 15 sponsored projects and a few projects that are in process right now that we're pursuing with some university groups. So this is us actually funding research in the university labs that is somehow aligned with what we're doing. We're not like directly coupling it. We're not delivering hard lists of statements of work and deliverables for components that are supposed to directly feed activities that we're doing at the Institute. But what we're really trying to do is foster some collaboration, helps promulgate these ideas about how to do larger scale robotics research. And improve our engagement with these organizations. So obviously we have some activities at MIT. It helps that they're about 2 blocks down the road. Activities that are going on with a group at Brown University, basically focused on cognitive knowledge and understanding. A couple learning activities that we're funding out at Berkeley. Another sort of learning for mechanism control effort that we're funding at Stanford. We have some ongoing discussions with old colleagues of mine from Carnegie Mellon, We have an activity going with people in Zurich that's focused on learning for control in general and specifically for locomotion problems. An activity at Yale focused on the design of dexterous mechanisms for doing manipulation problems. We have an activity with Michael here for University of UPenn focused on manipulation. And then we have a couple activities that we're talking to some people in Korea about. Here's the quick headshots of the various faculty who are actually collaborating relatively closely with us. So these are, as I said, these are the people who are spending somewhere between, I think the smallest engagement is like half a day a week. Most of these people are spending about a day a week with us. Typically that's done by, coming and spending 2 days every other week in our office. And then there are a couple people in here who are, more significantly committed at the 80 or 100% level and are really working very closely with us. Okay, that's it for the philosophy and the sales pitch. I'm going to try and talk a little bit about what we've done technically. Really, it's been about the past 6-7 months, right? So, we started a year ago. Took us about 5 or 6 months to get up to a critical mass of people who were involved in doing technical work in the environment. And then since then, we've actually launched a few projects. I'm going to talk about what those projects are and give you a brief overview of some of the technical work that's going on. So at the outset, about January, February of this year, small group of us sat down and said, what do? We have a bunch of funding. We're hiring a bunch of people. How are we actually going to structure them into projects? And we came up with this list of about a dozen projects that we thought were interesting for us to pursue. The ones in bold are the ones we're actually pursuing right now. The other ones are sort of in process. Watch, understand, do is one I'll talk about in detail. The simple description of it is, well, let's build machines that can watch, a whole bunch of caveats on what watch means, a person do a task, understand what that person did, and then be able to do that task themselves. Inspect, diagnose, fix is I should be able to send a machine into my factory, right? It should be able to have read or have all the knowledge that came out of my maintenance books and go walk around and look at the equipment. It should be able to recognize when that equipment is starting to fail and ideally fix that equipment. Ultra mobile vehicle is really about pushing the limits of mobility. Again, this is something we're doing. I'll talk about it in specific, but think about the parkour video I showed at the beginning as sort of a motivator for that. Robot creativity, aesthetics, and dance. I don't know that this is a deep technical topic yet, but what is important is getting to the point of having machines that can effectively interact with people. You've seen plenty of dance videos from Boston Dynamics in the last couple of years. Both Mark Raybert and I were involved with a number of those. And the one defect that they all have is that they are all robotic performance, right? They are scripted. The robot is doing something it was told to do. Sure, the robot is adapting to local conditions a little bit. But whenever you see 2 robots or 3 robots performing simultaneously, the only thing coordinating those robots is they're both watching the same wall clock and doing things synchronously against that clock. So they're not actually performing with one another. When you hear music and you go, oh yes, the robot's dancing in time to that music. Well, that's creative editing. The robots aren't listening to the music. They're not detecting the beat. So could we actually build robots that react to their co-performers? Could we build systems that listen to the music and interpret it and dance to the music rather than while the music plays? I think that's all possible. I think it's very interesting. We're talking to some people who are involved in, professional choreography and teaching dance and teaching performance and trying to think about how to do that. I know it's the thing I've wanted since I was a graduate student and started doing robotics is I want my personal assistant robot, right? I want the thing that can go do things for me in my house. I want to be able to send it down the street to the corner store to get my quart of milk, right? I would very much like us to have machines that were that capable. And so this is a goal for us, right? Competitive sports, right? Robot soccer has been around for a long time. It's basically become a programming competition, right? Who can build a better team? Can we actually build robots that are smart enough to really play soccer or be taught how to play another game, right? And so that's very, very interesting for us. The follow-on to the home assistant thing is, of course, helping people with disabilities. Let's build really capable assistants or assistive devices, right? Underlying almost all of these are capability for dexterous manipulation, particular dexterous mobile manipulation. So, if I had to critique the field of robotics, I would say, manipulation has made a little bit of progress in the past couple of years. Prior to that, I want to say it spent 10, 20 years making very little progress. And we'd like to shake that up. We'd like to do the very trite thing to say is we would like to do for mobile manipulation what we did for locomotion while we were at Boston Dynamics, right? So let's change the model and get to the point of having machines that are truly dexterous and truly dynamic in how they manipulate the world. We'll build some novel machines while we're at it. We'll work on these ethics and policy issues. If you're paying attention, we just had a press release week and a half ago where we announced that we're really launching our ethics and policy effort within the Institute. We're very interested in enabling the world to do better robotics research by providing some of the resources we have out to the academic research communities. So we have a notion of essentially providing what we'll call community cloud robotics. How do we give you access to our laboratory and experimental facilities as academic researchers and therefore help you up, your ability to do research at scale, do experimentation at scale? And then we're very interested in doing public outreach. How do we actually do more than just pop out YouTube videos? How do we actually engage with the public so that they interact with these technologies, understand what they're capable of, understand how they might be useful, help us see what the real use cases are? Because as technologists, right, we have a particularly biased view for what our technology must be good for. And the reality is when you put it in the hands of users, they will surprise you and terrify you. And it's really important to listen to them early on and figure out what they're doing. Okay, so what does watch, understand, do? This is a bit of concept art that sort of explains the idea. Person doing task in a factory, robot watching them, interacting with them, maybe being coached by them or listening to them provide a description of what they're doing, much as an apprentice would do with a master craftsperson. After the robot's done that for long enough, the robot should be able to go do the task, right? So let's replace the robot with a person, or I'm sorry, the person with the robot. And ideally, once I've gotten one robot to be able to do this, I should be able to transition that capability to a robot that has different morphology, different capability, and its understanding of the task should be generic enough that that new machine is capable of performing that task. And I don't care if we do this in an industrial setting, we should be able to do the same thing in a home setting, right? So I should be able to teach my robot how to cook dinner, and the robot should be able to turn around and cook dinner for me. So how are we going to do this? Well, this is one of the first places we're going to start by looking at basically using language models as an initial entry into this space. And what are we trying to do? The very simple tasks we're going to focus on initially are basically focused on bicycle repair. So we said, what's a simple mechanical thing we can get the robots to interact with? And we said, bicycles are pretty nice. They're complicated enough, but also simple enough. And they're easy to move around in a lab, don't take up a huge amount of space, don't have to worry about going to a car factory to do it. And so the simplest type of task is, let's fix the bike seat. Let's remove the bike seat. You can feed that into, any of the modern large language models with the right sort of preconditioning, prompt engineering, and get them to pop out things that look like commands that you'd like to give to your robot, right? Things like grasp the bike seat, right? You can have it's easy enough using sort of modern vision technology to ask a vision system, where is the bike seat? Has the robot grasped the bike seat? And then, what are you going to do? One model for this is to essentially precondition those language models with the programming interface that we have to the robot. So basically give it a list of skills, capabilities that that language model can use when it generates its outputs. Sounds like a great idea. Okay, let's see what we can do. Here's a short video of a spot robot with really nice vinyl wrap on it, not that silly yellow. And look, it's grasping a bike seat. How did we do that? Any guesses? Was it what I just showed you in the previous slide? None of the interns are allowed to answer. No, this was teleop. So the robot can do it. That's important, right? Why did we teleop it? We wanted to convince ourselves, yes, the robot is capable of doing this. The person who teleoped it, hid around the corner, didn't look directly at it. They only looked at the information the robot had available. So, we did it as a moderately fair test. What happens when you ask one of these modern machine learning trained systems, find the bike seat? We'll give you that picture and say, find the bike seat. First thing that comes out is all the red stuff. Why is that? Because those are all good places to sit. The particular model that we happen to use thinks that floors are good places to sit, and it associates the word seat with places to sit. And so it says the floor. That must be the bike seat, because it doesn't really know what bikes are. It just happened that it didn't have a lot of data about that. So using these large language models or large vision models or any of these things that are sort of generically trained, you need to be sure that you're providing good context for them, that they are being focused on the salient elements in the environment, right? So the first example was like, where's the bike seat? Well, okay, if you just use this visual language model, you get the seats, which happens to be the floor. If you tweak it a little bit, you can get it to actually pick out the bike post. I don't quite know why it does that, but you can also get it to pick out the bike seat, right? So yeah, it is in there that it knows the right thing, just the way the particular Bayesian weights came out, it happens to prefer picking the floor at the first try. So if we can add more constraints to this, sizes, locations, basically preconditions that we know ought to be true about a bike seat, then we can, rule out the seat post, we can rule out the floor, and we can actually go ahead and, pick the bike seat as the thing that we actually want to interact with. Excuse me. Okay, so it's possible with some extra bits of guardrails on the system that you can get those language vision models to actually pick out the right objects and then probably be able to work with them effectively. But if I'm going to do bike repair, then I have to actually touch things and I have to apply forces and torques to them, right? So the question is, what does it mean to tell your robot, I want to tighten that hand tight, right? Here's video of a person, turning a bolt to about hand tight. But how do I tell one of these models what that feels like or what information it should rely on? Am I going to be able to find that information on the internet? Our conjecture is no, we're going to have to do some work to build these models and find all the data to make that possible. So we're actually doing a whole bunch of research in-house about how we can use vision data combined with a smaller set of force and torque data that we're acquiring in-house to build models that would be able to deal with problems like this. That immediately leads us to the next project we're doing, which is this dexterous mobile manipulation problem. It's really, how do we build machines that can reach out, touch, interact with the world? How do we tighten bolts to hand tighten? And what do I want to do? I want to tidy the living room. I want to repair a piece of equipment. I want to be able to do the cooking tasks. I want to be able to repair equipment in your home. I want to do automotive assembly operations. I want to be able to wash your car, right? These are all things that require a level of dexterity, force interaction that's well beyond what we're capable of doing currently. Excuse me. So what are the challenges in this space, right? We really need to do contact-rich dexterous manipulation. We need to do more than just carefully pick things up and place them, right? We need to build machines that are going to be capable of using their hands, using their arms, using their bodies to interact with their environments. These machines need to have a capable level of task planning that reasons not just about the geometry, but about the forces and masses and dynamics of the environment that they're interacting with. And we need to make these systems smart enough that they can solve all the, what I'm going to call navigation and search problems that happen around doing any of this interaction. If anybody has ever worked on a piece of equipment or a car, how often do you fumble through your toolbox to get to the thing that's, under the other stuff, or that you put down and have since put something on top of, right? These are all things we take for granted. Whenever we build, industrial robotic systems, we engineer the bejesus out of them so that those problems don't happen. If we want the robots to really work next to us in our world, we have to get over that, right? We have to make them capable of dealing with some of the chaos that we put into the world. So we're doing some basic tasks on traditional pick and place grasping, right? And then we're doing things that start to look like whole body manipulation and starting to couple that with efforts to do it while we're being mobile. One of the first things we're working on is trying to connect a more informed visual language model up to a semantic grasping system so that when you tell the robot, go grab the bike seat, it does the right thing. And it understands how to solve the geometric and force problems associated with properly grasping the bike seat with an understanding of what you're going to do to it. If you're trying to pull the bike seat out of the post, you're going to grab it in a different way than if you're trying to align it correctly to the bicycle. A key part of this is what we'll call arm level dexterity. You could also call this finger level dexterity if you want to talk about doing in-hand manipulation. Really, it's about these sort of contact-rich manipulation problems where contact is going to occur in a variety of ways across the entire extent of a mechanism. So it's not just about the fingertips touching the object. Thank you very much. Yeah, I'll leave that there. Here's just, short little video of relatively basic, arm scale manipulation, right? Twist the bucket. That's our friend, Mr. Bucket. Nothing wildly fancy compared to the current state of the art, but again, we're excited to have the experimental apparatus in place in our lab and the instrumentation around this to collect all the pertinent data efficiently and effectively. Where do we really want to be? I'd really like to be here, right? Here's a well-trained dog moving at speed through an environment, solving a manipulation problem at the prompt of its human trainer, right? But I should be able to have robots that do that, right? And the interaction between the robot and the user operator should be as simple as the interaction is between this trainer and their dog. Okay, last project area that we're working on is this thing that we're calling the ultra mobility vehicle. So I showed you the video at the beginning with human parkour. The thing we're interested in here is slightly different. We're interested in what we're going to call this hybrid locomotion scheme. There's a sport called trials bike riding. Go look it up on YouTube. There are truly amazing videos of people riding slightly specialized bikes over extremely difficult terrain. How do they do that? They do that by riding their bike occasionally as a normal bicycle with two wheels on the ground, but most frequently they ride it as a unicycle with either only the rear wheel or the front wheel on the ground. The control is obviously through the brakes and through pedal motion and control of their mass on top of the bicycle, right? So why is this interesting to us, right? We've done all this work over all these years, building all these balancing robots. Why in the world do we want to do this? Well, we think that this sort of hybrid style of locomotion really gives us an opportunity to unify all of the things that we've learned over the years about locomotion and the control of body inertia relative to balance. So that's a huge motivator for this. What are we trying to do? Again, artist conception. We're going to build essentially a bicycle robot with all of its mass distal from the wheels. And that machine is going to do its best to hop, jump, balance across really complicated terrain. We have a prototype of that. So for those who are in the market for push bikes for your toddlers, Specialized sells this little thing. It stands, there's no scale here. The thing stands about 2 feet tall. It weighs something like 2.5 pounds. It's a beautiful piece of engineered carbon fiber. Gives a great basis for building an initial prototype of this type of vehicle. So we've bought a couple of those and then turned them into robots, right? Basically by outfitting them with a couple actuators and some computational and power electronics. Where are we right now with that? Well, here's our first prototype. It's doing jumps. This is not particularly well controlled at this point. It's just a little bit of torture testing we actually did the first week that we got this put together to convince ourselves it wasn't going to fall apart when it started to jump. But hey, you can do that. Not a lot of resources required, relatively straightforward. And we think that's a key first step towards starting to make progress on this effort. The next thing we're really focused on is that jumping part of the problem. And so this is what we refer to internally as Project Boing. And we have a simple prototype of that in process. Goal is to get to the thing you see on the top left. The thing you see on the bottom left is the first thing we built, which is just a very simple jumping mechanism. And then here's just a relatively accurate physics simulation of what we think that looks like in operation. Of course, my video won't replay. But with realistic actuator designs, we think it's totally reasonable to build this, basically a little bit over 0.5 meter tall machine that should be able to jump onto and over meter tall obstacles, drive like a bicycle, balance, really be a start towards doing that type of trials bike riding. Where would I like to be? I'd like to be building machines that, could really help people. In this particular case, we're thinking about people who have mobility disabilities, disadvantages. And how could we actually build a machine that gave them the confidence and capability to go into complicated terrain with their capable dog keep up with their dog and be able to navigate in those types of spaces. So we think that this project is actually a key enabling technology to get to that point. So again, I'm going to wrap up here. There's your QR code. There's a lovely picture of our building. We're on the 4th, 5th, 6th, and 7th floor. So the stuff that juts out with a little bit of green roof, and then we're a couple floors above that as well. And I'm going to stop there. Happy to take questions.
This is working, right?
Yes.
All right, perfect. I'll start with one of my questions and then I'll go around to the audience, weave in some questions on Zoom. So over the course of your career, you have worked on a menagerie of robots. Which one gave you the most joy to work with?
There are two parts to that, two answers to that question. The one that was the most pleasure to work on for the prolonged period of time was easily the fast running outdoor cheetah robot. The thing that made that fun was that every time we talked about what we were going to work on or what problem we had to worry about, there was one question we asked ourselves, which was, is this going to make the thing go faster in the next month, week, day? And if we could say yes to one of those, we'd go work on it. If we couldn't say yes to one of those, we're like, nope, we're not going to do that. So it was really an easy project to manage. The thing that was most satisfying whenever it worked was the hopping robot, the thing called Sandfleet, the little four-wheeled thing that could jump on top of the two-story building, right? That machine could jump 10 meters in the air. Every time it jumped, it was just like, oh my God, this works. Very joyful. It was in back.
Oh, okay. Quickly, I'm sure a lot of other people have much more technical questions for you. I was just wondering, because I was interested in the Work See Do project you were talking about. And I was wondering how that aligns with the ethics planning. Because the example you gave was watch a mechanic fix a car, and then the robot steps in and then becomes that mechanic. And in my mind, I saw that mechanic becoming obsolete. I wonder how on your end you envision that project working out.
Correct. I think the key point is we want to make it easier for people with not robotics expertise to have access to use robotics to do their jobs more effectively. There are lots and lots of industries where to be frank, the jobs suck. People don't like doing them. They do them for 6 months and then they quit because they're dangerous, wearing, not enjoyable. If we had robots that were capable enough and easy enough to program to do those jobs, that's going to help society, I think. And so, no, the idea is not that the robot is your big brother observer, watches you and figures out how to replace you. Rather, the robot becomes your partner and lets you be more productive and more effective. So I think of it more as an apprentice model than a replacement model. But again, these are important questions, and these are things that we have to engage with, actual users about, because I can tell you how I imagine it happening, and yeah, the reality will inevitably be different. Yep.
Curious for the skill-based projects, so watch, understand, do, or inspection.
For those capabilities, how coupled with the platform do you intend them to be, or do you think they need to be tightly coupled, or is there a path where you can throw it on any platform?
I think that's a super good research question. I think if you ask people to solve the problem right now, they would solve it in a very coupled way. I want to assert that it should be possible to solve them in a slightly decoupled way, where understanding a task is not necessarily tied to a particular mechanism, morphology, or capability, but is something that is, generic, right? The reality is that, we're going to have robots or systems that have almost disjoint capabilities, and it may not be possible to translate performance across those really disjoint capability sets. But if I do have two machines that have comparable capability, then yeah, it should be generic. But this is a hard problem, I think, and it goes very deeply to the question of what does it mean to understand a task, right? If you go pull up ChatGPT and say, how do I change a tire? It'll give you this list of things to do. Or the data that it was trained on has decided what the granularity of that is, right? Almost assuredly, ChatGPT is not going to tell you how to correctly torque the nut so that your wheel doesn't fall off, 10 miles down the road. A good mechanic knows how to do that. Where should that information be, right? And I think there are a lot of really interesting questions in there that we're hoping to explore by starting to build some of these systems. If you want to just, I can repeat your question if you want to. Yeah, if you want to go ahead, I'll.
I talked to a lot of people working for reinforcement learning and AI robotics, and one thing they talk about is they think intelligence may be overrated, and hardware is the true bottleneck, right? You didn't really touch on it, but what are some of the ongoing research or breakthroughs in hardware, materials science, or even physics that make you excited? And why?
Right. So the question was, people who are involved in RL and machine learning think that, grossly speaking, some of intelligence may be solved, and that the limitations are capabilities and performance of hardware. What excites me, or where do I think the opportunities are in materials, hardware, and the like? I think that's actually a great question. I don't quite buy in. I think there are still some very difficult open questions on the intelligence side of the problem. In particular, so historically, there's always a gap. There's always been a gap in robotics between the people who do top-down robotics and, sort of stop at symbolic reasoning, and the people who do bottom-up robotics and stop at control systems, right? We've never really effectively closed this, what I will call the signal to symbol gap, right? And it's tied directly to the language that comes out of ChatGPT or your choice of large language models, that it'll say, do this, do this, do this. Well, how do I tell my robot to actually do those things? The thing that I think is really interesting is to think carefully in the context of what are the languages I want my machine to understand, and what are the mechanisms that I can design that make that language more directly translatable to what the machine can execute. So things like thinking about passivity and compliance in a way that is targeted at enabling task execution is really important. So a simple example of this is, right, okay, we've all seen robots do grasping tasks, right? And the robot goes, grasp, right? Blindly move thing, right? That's not how any of us pick stuff up, right? We pick it up by grabbing it. We do this constant set, this large number of contact and impact events as we transition something from being at rest on a table to being grasped in our hand. And then once we grasp it, we probably do a little in-hand thing to make that grasp more reliable. There's a huge amount of pretty creative mechanics in your fingertips and in your hand that let us do that reliably, right? And we haven't figured out how to mimic that at all. And so I think, you know, there's a class of problems there. There are similar classes of problems in arm design and how you posture an arm so that you get good strength and good passive properties. The simplest thing is, you know, when you're doing grasping tasks, you want very low contact inertia in your fingertips, right? I don't want my fingers to knock the thing I'm grasping halfway across the table. I want my fingers to be very, very light as seen by the world that they're touching. However, once I pick the thing up, I want my fingers to be stiff, right? So that I actually hang on to it. And that's a design problem that touches on actuation, mechanism design, materials all simultaneously. And I think that's like a super interesting space. I think some of the opportunities we have with multi-material printed technologies helps us explore some of that. So I think I'm very excited about that. There are also some, I want to call them new ideas. They're not really new. They're pretty old, but they're rediscovered ideas in transmission design. How do I build the things that connect my actuator to my finger? In particular, some ideas about how to use what are called hydrostatic transmission elements, ways to do that transmission with fluid that can give you some of these properties where you get things that are both very light at contact, yet capable of exerting high forces.
Um,
Sorry.
So I'm gonna bring us back to the like watch, understand, do. When you think about what makes like a good employee or a good apprentice, it's a lot of, you know, curiosity and adaptability and sort of understanding whatever task you're teaching fits into like the larger context of an organization. How do you think about like the role of you know, not just being able to understand what's going on with a task, but bringing some more contextual awareness, adaptability, and curiosity on the part of the robot into that task setup?
So I think that's a really interesting question. I think it's slightly outside the scope of what we are trying to do. I think what we're trying to do is close this gap between the mechanical capabilities of the machines and this low-level execution reasoning problem. I think if we can do that, then there's sort of an unlimited ceiling of how much intelligence or reasoning you can put on top of that. And so I think if we are successful, then we will enable others to start to do effective research on those types of questions. I also think that trips a whole bunch of ethical and sociological questions that you know, we will as a group need to be attentive to.
The question from one of our virtual attendees. What is your view on the foundation model approach towards solving robotics? There are recent works that show that you can collect a huge amount of diverse robot manipulation data to train a transformer model. And through this approach, robots can learn robust and generalizable policy. Is the AI Institute interested in this direction too?
We just launched an effort that I didn't talk about today to pursue exactly that question. So yes, we are interested in it. The caveat I have is that all the work to date has focused on what I would describe as geometric tasks. All the reasoning is really about where to touch or what orientation to touch in. None of it has yet addressed these questions of how do I exert the appropriate forces on something. And so what we are trying to do is connect with some of those existing foundation models, looking at ideas related to basically video foundation models, and then trying to connect them to force-based or force-mediated task execution. So yes, it's an interesting question. Yes, it's something we're working on. I have a little bit of skepticism about where the state of the art currently is with regards to really solving this this problem of closing the gap in terms of doing what I'm going to call real manipulation tasks.
Awesome. Hi. So I guess the question is, I know the current state of like motion planning from Waymo and like vision programming for pipelining is sitting around 60% accuracy, and combined with like some of the non-determinism and lack of robustness in language models for prediction of like even for any prompt, how does that fit in with like planning for bike seat repair? Like, is that lack of stability in output, does that cause issues?
It certainly causes issues. I think, you know, we've been looking at things that are doing better than 60% sort of accuracy. And the other thing that we've been looking at is trying not to use these systems in sort of a one-shot way, but to use them in a recurrent way as elements in, you know, feedback systems or servoing systems. With some filtering applied to them, which helps, right? As long as you're not in a situation where they're constantly spewing bad results at you, you may do better. We're also very, very interested in how we build versions of those systems that understand and can output meaningful confidence information about how they're doing, right? It's not enough to say, I think, you know, with the best probability, that's the thing to go do. I really want the system to tell me, well, I'm really not very sure that I know what I'm doing here. And then I can ignore its data until hopefully we find ourselves in a better situation. But I think it's a great question, and it's a very important problem.
We'll have two more questions.
Thank you for the talk. You seem to present a lot of opportunities in working with the robot working with humans. I wonder, but there seems to be, I guess, relatively less number focus on that from the 10 thrust that you listed. So I wonder what you see as the challenge in the interactive autonomy case with humans.
Right. So, you know, our perspective at the AI Institute is that, you know, we're trying to solve the problems that are going to matter 5 or 10 years from now. And we think it is important that if robots are going to be well adapted, they need to be in closer proximity and more accessible by people. To date, that has not been true, and I'm going to say it's, you know, it's a chicken and an egg thing. Nobody's going to put the robot near a person because the robot isn't trustworthy, reliable, capable enough. So we have to make them more trustworthy, reliable, and capable. Can we take advantage of them being in proximity to people to achieve that? Well, if the person can serve as a coach, guide, guardian for the robot, then possibly. And so I think it's something that we have to sort of simultaneously address, the sort of user interface parts of it, as well as the safety, trustworthiness, and reliability problems, so that the operators, users can be safe. You know, robots fundamentally, if they're really going to succeed, if we're really going to help change the way society does physical labor, need to be able to be close to people. That's my, you know, opinion statement. So that's why I think it's very, very important. I think because of the situation we're in at the AI Institute, we can afford to think on this sort of longer horizon, or with a longer horizon perspective about how we address those problems.
Our last question is from a virtual attendee. Do you see successful output of the Institute being in terms of papers, milestone demonstrations like YouTube videos, or products / companies incubated?
It's a combination of the milestone demonstrations that are meaningful. And if a few of those milestone demonstrations turn into a spin-out organization or us licensing some technology to some other sister organization that goes and pursues and turns those things into a technology, I think that's, you know, a product technology. I think that would be absolutely great. Papers are great. We're going to write papers. Papers are not our measure of progress.
Following the fall break, we don't have a seminar next week. We'll have the next seminar a week after next Friday. It'll be Professor Leslie Cabling from MIT. So I encourage everyone to come back and hear what Leslie has to say. I think she's also been a visitor.
Leslie is one of our collaborators.
Yeah. So, you know, thanks again. I'd like again to thank Al for this very, very exciting talk. And, you know, go there, be an intern, and then become a faculty member at a university. And
then quit the faculty job and, you know, make YouTube videos. Thank you, everyone.